Okay, let's get going. So last week we made various parts of the code required to make fire stairs, pardon me, or any stairs. Um, but there is one thing that we sort of skimmed over, and that is how to actually work out where to put your fire stairs. So, um, what you might find is that you, because of the way that an architectural design um, comes together, where you've got setbacks, you've got your target FSR, you've got a maximum height, etc., that it's very rare that you design the footprint of your building uh, completely considering where the fire stairs will be. Um, it's tricky because you're trying to get the maximum area, but then at the same time, your fire stairs need to be placed in a location that's safe. Um, so that 40 meters, etc. And you've also got the issue of, usually you've got your core attached to that, etc. So in this particular job, 11 Eagle Street, which is done by Cox, you can see that we've only really needed to put in 2 fire stairs. Uh, so the minimum. It's a scissor fire stair, so there's an entrance on the left and on the right here, and but because of I think the floor plate being so large, they've had to put the fire stair on the center side of what is the services core. So there's a bunch of service lifts, regular passenger lifts, and storage rooms, male, female, and universal access toilets, etc. So there's the thing is, someone had to sit down and work out where this fire stair had to go. Um, and I'm going to talk to you guys about the tools that I would use to do that analysis and make that decision. And I did mention this early on in the course, but there are this process of in urban planning of analyzing how long it takes to travel called an isochrone. And this method of mapping out a city or an urban plan gives us a good idea of potentially how much foot traffic there might be from train stations, or how long it will take to get a telegram from one part of France to another, or if you're if you're someone very interested in buying property but also wanting to start a family, how many public and private schools or playgrounds are in an area within 10 minutes of a walking point. Blah 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 blah. It's it usually associates time with distance with time. So in this case, like driving a car takes 10 minutes to get from point A to B. I don't think this one's 10 minutes though. This looks like it might be hours. And but this all sort of falls back on creating a model of your space that is analyzable through certain systems. Um, and so that system is called a graph. We're so used to graphs being sort of described mathematically, like it's just a two-dimensional space that, or three, or whatever, that plots information or mathematical formulas. But if we look at graph theory, It's the idea of a mathematical model where you have nodes and those nodes are connected, um, and they can get very complicated, like so. But at the same time, like does this particular graph here, this for graph theory, remind you of anything? Pardon? Trees and branches? Yeah. Hang on, let me pull up another one just to let's pretend this is a graph. Do these graphs remind you of anything? They're trusses, right? So you guys have already used graph theory in a way by using Karumba. What Karumba basically needs the models that you produce to be fed into it to work like graphs. Can you use curved lines in Karumba? No. Can if I had a straight line that went from here to here and it ignored these 2 points, so it passed by them, Karumba doesn't know that there is a physical connection between this bottom flange and these inner web sections. So this idea that you've got nodes with connections exists with Karumba. Karumba maps that out. You put a force on the nodes, and the force will travel down the graph through the connections from node to node to node until it gets to a node that it knows is what's that, an anchor point. So like you've restricted its movement. So in this case, you might say that's that node there and this node here, and it basically does all the standard maths that an engineer might do, taking into account vectors and whatnot through those connections to know how much a member is being utilized and in what direction it's being stretched. Is it being put into bending? Blah 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 blah. So graph theory has already helped us out with structural analysis there. There's these other things that we use quite frequently now. It's almost an obsession of some people that regularly relies on graph theory, and I'm just going to sort of not prove, but talk about why it works. So most of you are using social media. Is anyone here friends with any other person in the class on Facebook? No one. Okay. I'm sure someone is. I'm sure I've seen Paolo and Emilio are good friends in person. They seem like they might be Facebook users. Social media graph. The one thing that I find really interesting about users on Facebook, some people think they can kind of use Facebook but not give Facebook any information. So, like, Facebook doesn't know how to advertise to you if you don't give it any information, right? So you could be using Facebook just to message other people. You could be here. This is great. So let's say I'm Carl. I've got a little bit more cool in my style. You know, I've twizzed up my hair. I'm wearing a yellow shirt, and I've said, you know what, I can stay zeroed with Facebook. I'm just going to use it to chat to my friends Eliza, Diana, and Bob. Facebook isn't going to know anything about me other than that I'm friends with Eliza, Bob, and Diana. And if all Facebook did was know that I was who I was, and they didn't know anything else about these people, they couldn't really advertise to me. They couldn't sort of predict my behavior, blah, 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 blah. But when you are friends with Eliza and Bob and Diana, you don't have control over what they're doing on Facebook. So Eliza could be, and you're probably friends with people that might be interested in the same things as you. So Bob, Diana, and Eliza, you know them through hiking. Like you just love going hiking with them, and they post pictures of hiking. They look up stuff on Google for hiking, and Facebook knows because there's wrapped containers in there, and blah 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 blah. Like basically, all they care about is hiking. You haven't told Facebook anything about hiking, and yet Facebook knows to advertise hiking to you. Do you see why? Because you've got these connections going, right? If I can't have connections going from one, like a person to nowhere, and this is kind of like why this kind of helps understand Crumber a little bit. If I had Eliza connecting to another person in between Bob and Carl, the system, like I could drag that out, and the lines cross, just like this Diana to Anne and Eliza to Carl connection, but it's not a connection from Carl to Anne. Yeah? So what we can do is we need to build decent graphs of lines, and sometimes people build them just through saying, okay, well, here's 10 people. We don't actually have to place them physically, but we just need to create a map of who's connected to who, and from that you end up with your graph. So if I then go back to this problem of you've got a floor plate, how do you place fire stairs on a floor plate? We can build a graph that describes movement on the floor plate. So we can say someone might move along this point and say we'll just limit that to 1 meter segments, and then they might move another 1 meter, and so on and so forth, and so on and so forth, and create a network of walkable connections across the floor plate. Then we can say measure the distance it takes going from node to node, just like measure the force applied at this point, what it becomes as it moves through the structure, or measure the advertising impact or influence on interests of friends in a social network. Measure that distance to any other point to work out how good it would be to place a fire stair at this location. Does that make sense? Good. Okay, Jason understands. That means everyone understands. Good. Does that not make sense? Does anyone not understand what I'm talking about? I'll give you 3 seconds. 2, 1, 0. Okay, good. So there are various different ways that we can create graphs. In theory, Grasshopper already deals with graphs in vanilla. You don't need a plugin. You can technically write it all using their components. It's really complicated when you want to start doing graph analysis. So One really useful one that I've found over the years, and it's probably quite old now, but it's doing its job, is Spiderweb. So if you guys can try and install that um, now, because we're going to use it very soon. Use the latest one, 2.3. Oh no, hang on. 3, 3.2, 4.2. Use 4.2. Only because look, like I'm using this I've been using this in Rhino 6 and Rhino 7, and it still works. So the one thing that's, I guess, really interesting is they very rarely change the sort of engine of Rhino. So yeah, this should work. And what we're also going to do is we're going to open up Revit, purely because who knows, someone could have given you a Revit floor plate to do this analysis on. They could have put a fire stair already on that floor plate and asked you, hey, can you work out if this fire stair works? So if you open Revit up, let's draw a big floor plate, and let's also make sure that it's, big. So I've drawn this to about 50 meters on either side, and I've made it slightly interesting. Whilst you guys are starting Revit up and installing Spiderweb, I just want to throw one other sort of discussion point at you. If you look at this, no, that's not a bad graph. It's a bad one. If we look at this graph, we won't edit. I'm just gonna close this graph off for a second. Like that. So if we look at this particular graph, does that remind you of anything other than a structure, other than, a walking path or whatever? Does this look similar in any way to a geometry class in Grasshopper? If I, if I, pardon? You're right. It does like a Voronoi, but like it looks like maybe it's actually the inverse of a Voronoi. But what like a Voronoi is not an object class, okay? So Voronoi is like Voronoi produces curves, right? So if you think point, line, brep, blah blah blah, those types of object classes, does this one remind, like, just think about it. How many sides does each parcel? Yeah, so it's a mesh, right? It looks like it could be a mesh. And if I whip open Grasshopper, are you guys picking up the background noise that in my place or not? Good. Okay, good. The noise cancelling is working. So if we had a mesh, and I'll try and make this as simple as possible. Where are we? We want triangulate. Okay. So we've got this mesh here. We can of the sort of new second years. Have you guys have learned a little bit about meshes or not? Yeah, yeah. Okay. That's good because look, like meshes are great for they're great to represent things and they can do really complex stuff, but they've like if you use meshes at all in your like in a design process, it's very hard to come back from them. It's usually a one-way process. But in this case, I'll just show you what I'm talking about. This mesh here is made up of vertices when I break it down. It's just a cloud of vertices 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And it's just like the polygons are just a series of instructions on how to connect those vertices. So in this case, there's a polygon that goes from 0 to 1 to 5. So 0, 1, 5. And if I turn that mesh back on, there it is. That 0, 1, 5, 1, 2, and 6, 1, 2, and 6, 4, 5, 9, 4, 5, 9, etc., etc., right? So usually meshes follow graph theory rules. To begin, like, it's very hard to you can't make a mesh that doesn't follow the graph theory rules. What graph theory does allow, though, is it does allow you to make a graph that looks like this. So, a mesh can't do this because meshes require, that a bunch of nodes at least make a triangle. You can also do this with a graph. So in this case, that would be a broken mesh. It would be you can make a mesh like this, I think, but it would be considered a mesh with an inappropriate valence. But the critical thing here is it's kind of like saying, okay, as long as we have a rectangle, the system will work. And then we say, well, we're only using squares. Squares will always be rectangles, right? So even though we're allowed to do, this rectangle or this rectangle, we're going to make squares. So we're guaranteed to always have this work. So if we make a mesh, we'll be able to use that mesh to make a graph and therefore make an isochrone. So that's what we're going to do. We're going to, rather than spending quite a lot of time mapping out how people might walk, how people might walk from, this point to this point, so on and so on. We're going to take this whole floor plate and just turn it into a mesh. And that mesh will work for our isochrone graph. So, can someone, is everyone up to the point that they've got Revit open, they've drawn a floor? Do I need to keep talking about stuff, or so we need at least a floor slab drawn? I'm gonna make this one reasonably modeled because at the moment it looks like it's timber. Let's make this like a concrete. Can you put up your hand if you're ready? Is there even a hand putting up in this? Ah, so when you hang on, I'll do it for you. As in, I'll run through it. I think you will need to reopen Revit if oh, what's going on? Spider web. So, oh yeah, yeah. So, once it's installed, Jason, you've installed it properly, right? Okay. Okay. Well, I'll just if you did do that, just check under the tab extra. Do you see anything there? Cool. Okay. So that means it's not there. So Um, there is a there is another way of installing stuff. There's actually a few ways, but the dragging method doesn't always work because it doesn't. The DLLs might need to be installed. So like Grasshopper doesn't know where to put these. So let me just unzip this. So if you go back to Grasshopper, in the if you have specials components folder. It's this folder, and you can go into your users user folder in your app data through roaming, Grasshopper, and libraries. So that's why they've given us the nice shortcut. If you copy and paste that these files into that folder, and I'll just do that now. And then also just make sure if you right click each of the files that you have copied, there's a Windows security method that if someone's put anything dangerous in there, in the actual DLLs and the code, um, they're blocking it from running. So you have to right click each one and go to properties and unblock. I can vouch for Spiderweb. It's not going to do anything dangerous. You have to do that to I think each of the files. Just double check them and then restart Rhino. And recently, Rhino 7 has also added this thing called Package Manager. So if you type that into the command line, um, it's because I'm using the internal Revit one, but you can potentially find the plugins that you're looking for through the Package Manager in Rhino instead of, you know, downloading them off Food for Rhino. I think there are hands. I think if you open up participants, reactions. Mine must be it's because I'm sharing. So we're still waiting on a few people, but that's fine. So is anyone else having trouble getting to this point? If so, let me know what the problem is, and I might be able to help. Hey Leo, how you doing? Are you guys in the at uni? Okay. With Tom. You're having a good time with Tom. Now I understand why there was that feedback loop earlier. Did you guys get my message or not? Sorry. You don't want me to be there in person, seriously. Yeah. Oh, good. Okay, well then you can help Tom out. Oh, and your microphone's working. Oh, okay. Oh, you're talking through Tom right now. Oh, okay. Tom's, yeah. Oh, good. Go for it. Go for it. Yep. Okay, we've only got 4 people who are ready. Um, Gary, do you need any help? Russell, do you need any help? Okay, Gary's ready. Amelia's ready. Jason, did that work for you? It did. It must have, because you've got your hand up. Excellent. Cool. So yeah. I'm guessing Leo's helping Tom. 1, 2, 3, 4, 5. You're ready. Tom's ready. Then put your hand up, mate. One, two, three, four, 5. 3 more people. Janlun, Justine, and Guan Lin. Do you need any help or not? Is it just, your computer's being slow or something? Yeah. Oh, okay, cool. So you're all done? Okay, cool. So we're ready to go. That's fine. Everyone can put their hands down. So what we're going to do is we're going to bring this Revit floor slab into Grasshopper. When we did the code a few weeks ago with Revit, we were baking stuff into Revit. Today, what we're going to do is we're just going to use the Grasshopper method of pulling information in simply. So under the parameters tab, you can see there's all these Revit primitives, and you can pick, floors and all of the like floor here. But one of the more useful ones is this graphical element. Grabbing that, you can right click that and go through and set one or set multiple. So we can go just set one graphical element. We can go pick that floor slab, and that will bring that into Rhino and Grasshopper. Cool. So that's giving us that geometry. this, let me just do a quick measurement there. Yep, that looks roughly like 56 meters. We then need to extract from this the geometry that describes the boundary of the floor. We can do that a few ways. The first is, just by simply going and grabbing the elements curve. Is that working? No, that didn't work. So rather, if that's not working, then what we're going to have to do is deconstruct this BREP to get one of the surfaces that describes the floor. Most slabs are flat, planar type things. Some aren't, but this one is. If I was to explode this, can anyone suggest a way for us to just isolate either the top or bottom surface? First we have to element drawing. So that's converting this into a BREP, this element geometry component, and then deconstruct BREP's giving us a face. Can someone suggest a way to get the top or the bottom? I've got 9. I only want 1. Okay, but if I use list item 0 is going to give me possibly the bottom one or the top one, right? Yeah, that you're thinking the right way. So if we use area, what else does area give us? The area that you can then evaluate like which 2 centimeters are the maximum area in the. Yeah, if we had a really small slab that was really thick, then the side would be the area, the higher area, right? One of the sides. We only need 1. We only need 1. What? Yeah, you could. But what area gives you something other than the area? It also gives you the centroid, right? Yeah. Did you get it? Centroid with a higher C. Easy. Yeah? So you can, if you just sort your faces synchronously by their Z value, the last face in that synchronous sort will be the top one. I'm going to put a panel in. My habit is to insert it, but yeah, there we go. So there's our top face. Yeah. Do you see what I'm like? This is really simple, just little thought process that when order matters, and you've got systems where deconstructing a BREP and you have no idea where the BREPs come from as well. We very rarely have control over what face comes first in BREPs. So when you join a BREP, the Rhino doesn't say what's the first one, what's the last one, pick all the ones in between. So we can rely on systems like measurement and analysis to sort and pick out the one that we want. Cool. Okay, so we've got a surface. Now we want to turn that into a mesh. And the stock standard way of doing that is with this component called mesh BREP. If you can't see these lines that this component produces, those mesh or polygon edges, then you can turn them on by going under display and turning on preview mesh edges. And what this component does from the get-go is it just tries to create a mesh with the least amount of polygons. So right now, if we were to use these connections to work out how to move through the office, then we could know what the distance is from walking from this point to this point to this point to that point is, and is that longer or shorter than this point to that point, so on and so on. But it's not necessarily going to help us get within the floor plate. And we then sort of move on to this idea of sampling. So when we do a lot of analysis on a computer, that analysis needs to be limited to some point, or otherwise that computer is going to be working for a very, very, very long time to actually solve the problem. So what's a good example? Other than this one, if I had a plate in 3D and I want to work out how much sun is hitting that plate, it's probably not a good thing for me to do to actually work out each photon hitting that plate, because there's billions, trillions of them hitting that plate, and doing the calculation, the analysis that way just doesn't work. It's going to take forever. We can simplify that scenario. The same sort of applies with this particular system. I could work out to the nearest millimeter where the closest point is if we divide this whole floor plate into little millimeter polygons. But a millimeter isn't going to make that much of a difference in a fire, right? So, and there's no right or wrong answer here. If we're saying that the maximum distance that we can be away from a fire stair is about 40 meters, can anyone have like a stab in the dark at maybe what they'd think a good sample size, so the length of a movement in it as a graph would be? Anyone? Do you guys know what I mean? Do I need to explain sampling a little bit more? To explain sampling a little bit more. So what we want to do is we want to create a graph going across this floor plate, right? This will be interesting. So if someone was like, if we were to pick this point here, that point would know the distance to get to this next point is 5 meters, and then the next point is 9 meters, and the next point is 14 meters. And we're going to analyze that point and say, okay, that point is 100 meters to this point over here, not 100, sorry, 20 meters, let's say. It's 100 meters to get to this point because it has to go along that wall and then along that line. But because we're using a graph system, there has to be these discrete hops from node to node. We can't, if we were to put a if we wanted to measure this distance, we have to put a node at that point for the system to be able to measure it. So we have to pick a sample size. And that sample size, if we made it millimeters, so every 1 millimeter, there would be quite a lot of points to sample. It would take too long to analyze it. And as well, millimeters aren't going to help us with this analysis, right? It's just too fine. So what, like, we're thinking about meters. You know, we're thinking 40 meters. What would be like a decent size for a sample? Dead silence. Okay. I think it would maybe be smaller than a meter. I'd probably go maximum half a meter. But if we had to be really accurate, maybe 100 millimeters, so a tenth of a meter. But in this case, what we'll do is we'll just stick to 500 mil. So this mesh BREP system, there are options. There's these settings. There's a component that lets you control them. You can put in sort of predefined ones like a speedy mesh or a quality mesh, but this settings custom component, which you can find here, lets you control a few things. And the one that we want to set to make sure that this is producing a mesh for our graph that's 500 mils is this maximum edge input. And that will quickly break down our mesh into little 500 millimeter squares. There's various other things that we can play with. You can see here the aspect ratio, it's set to a maximum of 20. If we want this to be a nice uniform graph calculation, we can force that to have an aspect ratio of 1. I don't think that's going to change much now that the maximum edge has been set. But if I delete that maximum edge, you can see it's rather than making the sort of just straight triangles, not straight triangles, just warped triangles, it's trying to force them to be squares. And there's various other settings here that are really good for more curved surfaces than anything. So like maximum angle or maximum distance that a vertex can be away from the base surface, etc., etc. One thing we can't control though is how many edges the polygon can have. So Grasshopper and Rhino, they only think of meshes as having triangles or quad polygons. So there's a four-sided one and there's a triangle. There are other programs that allow polygons of multiple sizes, but usually when it goes back into sort of like computer graphics, even four-sided polygons are converted to 3. So this four-sided one, when it's being rendered, is actually made up of 2 3-sided ones. So this mesh BREP component's just picking, okay, I'm going to make this 4, I'm going to make this 3 to make it efficient. What we can do is we can force that to be triangulated by throwing in a triangulate component, and that will at least provide these little crossovers. I am just saying now, as a word of warning, this is not perfect. So in any situation where we want to calculate, we might want to be able to cross at 45 degrees instead of in the other direction, rather than from left top to bottom right. But in this case, we'll make it work. The best mesh that we could produce across this would be one that is like a hexagonal grid. So, and I'll just demonstrate. So if we were to make, not hexagonal, sorry, equilateral triangle grid. So if we made a hexagonal grid very quickly and grab its points, and then use those points to make a Delaney mesh, this type of grid would be much better for this analysis. If any of you want to explore trying to get that to work across the slab, you're more than welcome to, but we're going to skip over that because it's going to take all lesson for me to explain that one. So that's giving us a mesh. We need to be able to turn that mesh into a graph. And even though I said that it is one, I mean a spiderweb graph. So spiderweb has multiple means of creating graphs. So we can turn a data tree into a graph, and we can make a graph from cells. We can make a graph from points, blah blah blah. But the two simplest ways of doing it is making a graph from lines or a graph from a mesh. So in this case, we could just plug our mesh into our system, into our graph from mesh component, and that will produce a spiderweb graph object. And it will also give us the vertices or the nodes for that particular graph. You'll notice there's like an EG here. If we right click the component, from a mesh we can either produce an edge graph or a face graph. So the edge graph here is telling us here's a node, which is the vertex, and that vertex is connected to this vertex over here. But we could also make graphs from meshes that describe adjacencies of polygons. So we could say this polygon here is adjacent to this polygon, it's adjacent to this polygon, and it's adjacent to this polygon. So just be mindful, that's why there's two options there for the graph. Cool. So we've actually jumped over quite a lot of steps to produce a graph just by using spiderweb. It's produced one. If we go and grab the display graph component and plug the graph and its points in and turn this on, is that gonna? Please don't crash. Good. What this does, actually, I'm gonna make sure. I think Revit's probably trying to display all of this. Let's turn that off. That's why it's running so slow. Okay, so what this is showing us is a pink lattice that is being represented on our mesh edges, and we can see there's like two curves that are being produced at each mesh edge. One thing that I haven't mentioned about graphs that apply, but not necessarily in this scenario, is that you can have a directed graph. So if this fire stair here, if it was a secure building, this door, you couldn't get through the door from inside the fire stair. You can only get into the door from outside. So it's a one-way door. So if I were to draw a graph that represents the movement in this building, not for fire analysis, but just to show movement, then I would have a node on this side of the door and a node on the other, and the node, let's say we'll say that's 0 and that's 1, then I could say, well, you've got a connection that goes from 0 to 1. But over here, this door that goes into this meeting room, we'll say node 2 and 3. I would have a connection that goes from 2 to 3 and also a connection that goes from 3 to 2. So the orientation doesn't seem like it matters for a mesh, but it actually does. It determines, like, when you have those connections and you have that orientation, it determines the actual direction that the polygon is facing. But yeah, just note that in this system, what the mesh is doing when we produce the graph is it's already creating a directed graph. If you've got a non-directed graph, a uniform direction graph, it's doubling up all the directions and flipping them. You can edit graphs and ensure undirected, and that will make sure that anything that only has one direction has two and ignores all the others that have two. But that's fine. We need this to be undirected because we don't want to stop someone from walking like backwards along a path if that's necessary for this analysis. Is everyone at this point? I'm going to turn off the display graph because all those pink lines aren't necessarily helping. Okay, so graph theory, it was initially invented to try, I don't know if it was, like, a lot of people sort of use this particular example as the invention of graph theory, but it seems a little too niche for it to work. But there's this place in Germany called Königsberg, where it's split by these rivers and there's these bridges, and people wanted to work out, is it possible to go for a walk through Königsberg, crossing each bridge but only crossing each one once. And so if you draw it from this island here, going across 7, 6, 5, I'm stuffed, right? 7, 6, 3, 4, 2, 1, I'm stuffed. So there's the process of then iterating through all the different problems sort of helps with this graph theory, because we've defined all the points, we can actually do the smart mathematical connections. Someone's actually solved the problem. Oh no, that's the graph theory diagram. So what we can do is we can use the provided tools to work out various things, and which means we don't need to kind of know the math that is required to do it quickly. So rather than sort of iterating through and finding thousands and thousands and thousands of calculations, instead what we can do is we can use functions like minimal spanning tree, shortest path between points, those types of things. So if we use the minimal spanning tree, no, we don't want that one. Single source shortest path. Actually, let's use minimal spanning tree as well. So plugging our graph into minimal spanning tree, what this does is it's very quick. So it's doing this over 7,164 nodes, and it does it in about 2 seconds. It gives us a graph edge list, and if we actually display, I think, this graph, what it will show, maybe I shouldn't have done that, is the like to if you were to walk down, if you were to get to every point, where those connections would be. So, and this one's gonna like this is just an absolute nightmare. But this is not taking into account the 45-degree angle. So you can see one of these points. Let's say it was this one. They've decided, well, to get from here to here is a short distance, and then to get from here to here is also a short distance. The reason we're not using here to here is that if we were to go back to that point, that's a longer distance than if we were to go down the first line. Does that make sense? So not a very useful tool, but at least it you're aware that it exists. So if, what that does is it works out exactly. There's a point somewhere, and it doesn't tell us where, unfortunately. But there is a point where that started for that minimum spanning tree. But if we throw this same function, this same graph, into a single source shortest path. Actually, before I do this, just to speed this up, I'm going to go set this to 2 meter. Shit, that's not 2 meters. That's 200 millimeters. My apologies. This might just take a minute. Is everyone sort of understanding this graph thing, or do I need to re-explain it? Cool. Come on. What is this? Using okay. Whilst we're waiting for it's done. Cool. Okay, let's make that 2 meters. Cool, that's much faster. Okay, so so with a single source system, we have to pick a source point, and what that requires is for it to be an index. We can't just plug a point in. So if I use this point here, it's not going to work. It's what we need to do is take this point and work out what index that is in this cloud of points, or at least what's the closest one. So if we use the closest point component, so here's our cloud and here's the point that we want to work out, and that's worked out that one's the closest. We can use the index from that to create that minimum spanning tree, and then we can use that to produce our graph. Is everyone getting, a graph that might look similar to this? Or not? Who's not able to get this to work? You might need you might need to go unblock. Is it like just go, if you go File, Special Folders, Components folder. Being weird. What components have you got? What components do you have? Do you have any of these? Right. Hi. Pardon? The points. So, can you share your screen just to show? I'll stop sharing mine. Yeah, that looks great. Yeah. So see, if you just preview your mesh. Okay, yeah. So see the way that this is meshed the system. No, can you also select the points in your cloud? Oh no, sorry, in your oh no, that's fine. Okay, so see these points. Even we don't need to see each line, right? We only need to see that each node has managed to get, we've been able to get to that node. So if you go back to your graph output, like so you can that sort of branching tree that we've made, it's every point is getting a line to it, right? It doesn't need to, right? Because to get from where your point is, we're taking the shortest path using your using the 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 mesh that we've provided to get to that point. Yeah, so like if I said okay, you know, you start, where's your point? Your point's kind of in the middle there, right? Yeah, you don't need to draw, like if you see that, if you pick any section that looks like it should have a line connecting it, like the one just above to the top right, up. See how there's a gap in between? There's a gap. Can I do this? See how there's a gap here? Oh no, don't move it. Go back. Okay, zoom in a little bit. Okay, so you can see there's a gap here, right? But the gap doesn't need that connection doesn't need to exist, because what we're doing is we're saying you need, like, it takes to get to this point here, the shortest path is along that line. And to get to this point, the shortest path is along this line. And if we want the shortest path to here, this line here, this connection, is a shorter distance than if you were to do this. Does that make sense? One thing one thing I've noticed though is here. Can you just jump to there in your script? Oh yeah, no, all good. It's all good. Excellent. Okay. So Yeah, you can. So we can see here there's this thing called a cost. And in this case, because we've used a meshes are naturally geometrical. Um, the cost is associated with the length of the line. So we've walked down this path, and it's telling us that we've walked 15 meters, for example. You can make graphs. Now, the cost is based on this thing called a weight. So for every connection that you have between two nodes, you can assign properties to that connection, and Spiderweb allows you to only assign one property called a weight. And so if we were doing an isochrone, like a one for like pedestrian movement, we would make that weight based on how long it takes to walk rather than how far you've walked, because there will be certain connections that have penalties. So you might have, crossing a certain road on a pedestrian crossing might have a penalty of 0 extra seconds, but then waiting at traffic lights might add an extra minute of time to your path. So just know that the weight and cost of these graphs doesn't have to be distance, but in this case we're using distance. So what that's telling us here is from this point there's a cost to every node, and if we just mouse over that, that's telling us there's 527 cost values that are being produced, and we've got 527 nodes in our network. So it's giving us a cost per node, and what we can do is we can map that onto our network using colors, using gradients, using symbols. So if I quickly go and grab the minimum and maximum bounds of our costs, which should be from 0 to 52 meters, we can use that bounds to recolor our values. So here's the cost going into the parameter value of this gradient, and we can plug in the start and end value of our measurements into that, and that should give us a color per node. And just to demonstrate really quickly, but we might refine this, if we use a dot display, we can plug our GP, so our graph points, into a dot display. We can plug a color into that, and we can set the size of that. We'll set that to 100 mil. Is that display? Okay, let's make it 300. And if we want to make this read a little bit better, we can set this to, like a heat map, hide everything, and just display that dot display. So as I move this around, you can see that dot display is working out very quickly how far we have to go with the maximum. So rather than using the deconstruct domain, if we instead say, okay, we'll set this to 40 meters, 1, 2, 3. Is that 40 meters? 40. Have I made this much bigger? No, it's 54 meters. 40 meters. Yep, okay. One thing you can do with this gradient is if you double click one of these points to change its color, you can set a discrete like flip. So we could set the right hand side of this black to be red, but the left hand side to be black. So when even if it's at 100%, once we get beyond the limit of 40, it'll go bright red in the system. Does that make sense? So if we had a fire stair here, that would only be able to cover this much of the floor plate. To do which part? The upper limit. So we've set the upper limit here as 40. If you double click on a point in your gradient, you can then set the left and right color. So I could set this to be blue on the left, and then red on the right, and that means that once we hit the upper limit, anything beyond that on the right of it in that gradient is going to be red. One thing I need to give you guys a warning about gradients is that the default settings for the gradient is non-linear interpolation. So it will be giving you a change of color that kind of does this, where there's like almost like a sine wave, so it smoothly gradiates from white through to blue in this case. You can force it to be a linear relationship like so by right clicking the component and selecting linear interpolation. So just know that you might be getting, if you don't do that, you might actually be getting information represented to you that isn't correct. Like for example, if we know that this sort of like faintish blue means a certain thing, it might actually be showing you something higher or lower, like a higher or lower value than what it should. Now, we've used dot displays. There are various other display methods. Dots are actually not that efficient because what Grasshopper is doing is it's actually rendering a sphere and giving it a color. There's a more efficient symbolic component called symbol display. What you can do is plug your colors into the either advanced or simple symbol maker, and like we get a size for that. This symbol I think is a tag, so plugging that into here, that's going to make some colored tags, and we've got it's making a bit of a mess, but there's a bunch of tags, but you can change how these look, whether or not they're circles or crosses or whatever. But we can also potentially use the mesh that we produced earlier to also display this information a little bit better. So in theory, the vertexes that we've collected here that are in our graph from mesh, you would hope that they are the same order. There's 527 vertices and there's 527 graph points. These are hopefully in the right order. So if we can deconstruct a mesh and get its vertices and faces, that means we can construct a mesh using vertices and faces. A few other things that it knows meshes can have mesh vertexes colored vertexes, And we can also get information about normals, but we don't care about too much about that at the moment. We can use construct mesh to basically put two meshes back together again, like so. We could technically grab these colors, plug them into the construct mesh, and we now have a mesh with our gradient colors assigned to it instead of like a field of points. Does that make sense? So we've got the order of vertexes is the same as the order of the nodes. So when we've tested each node and we're getting the colors, we're coloring that to a mesh, and the way meshes color with the vertexes is they'll create a gradient between the colors. So here we've got two cyans and the red. It'll gradiate across that direction and gradiate across that, and it just produces a nicer representation of that sampled data. Are we good? I've got people chatting. Andrew, could you go through the color settings once more? The gradient settings. You mean like from this point? Okay, so what we've done is we've done a single source shortest path. So there's a point that we've calculated. Hang on, I'll just make this a little bit more easy to read. Okay, so there's a point that we've calculated, and the system has gone through and worked out a pathway, the shortest path to get to every point in the system. So to get to this point over here, it's suggesting that you walk down this zone here and walk along here to get to there. That's not necessarily realistic. Technically, that is a much shorter path, but we have to work in a system that has some logic to it, some sampling logic. If otherwise, we're going to have to draw thousands of lines from every point to every point. So that's telling us it's not only telling us the pathway to get to each point, but it's also telling us the cost of how to get to that point, and that cost is based on the weight of the connection, and the weight in this case is based on distance. So it is telling us how long it takes through distance to get to that point. So it's giving us 527 values. That's 527 values for 527 vertexes in our mesh. So the gradient system, it takes a number, like a parameter, and it gives you a color based on a bounds. So in this case, this gradient, we are telling this gradient that there's a bounds of 0 to 40 meters. And so if the number sits in between 0 and 40 at 20, then it'll give us a yellow. If it's sitting at 75% between those two, it'll give us a blue, light blue, and so on. Like it's fairly straightforward. So the color that comes out of that, these individual colors, they represent the cost that is coming out of this single source shortest path, and we're mapping that into a reconstructed mesh, which will color the vertexes of our original mesh based on those colors from that shortest path. So that's why we're getting this system. So if I, just to demonstrate, if I slowly pull up the lower limit, you can see the gradient starts to grow from that point because everything less than 21 meters is now going to be red. So double clicking one of these points, we can change the color of the gradient. We can set the hard change from, in this case, left and right from blue. I'm going to set this to white on the right. So any white zone in our mesh is beyond 40 meters from the point that we chose, this point here. Does that help, Tom? Cool. So we'd be getting slightly more accurate values if we were using like a hex grid. If we were drawing straight lines to all these points, it'd be even better, but we have to sort of be limited within this. Plus, if we use this, the distance that this actually travels is this distance here is longer than that straight line distance. So you're gonna get a slightly safer analysis. So we're erroring on safety here rather than erroring on danger. So this at least tells us, okay, if we pick one point in the system, is it going to be good? But we now want to use this same sort of thought process to be able to work out maybe not how do we tell ourselves where the best system might be. I mean, because this one requires trial and error, but we could technically ask the system to tell us, okay, give us a good idea of where to put our fire stair entries. One thing I will do though, shall we make this so that it works on 2 points? Because we've got to put at least 2 fire stairs in this office floor plate. So let me just quickly turn this off. If I grab 2 points, and this works very similarly to a I guess the same way that a multi-pointed attractor script will work. If we plug 2 points into this, we're going to get 2 outcomes in 2 different branches. So if we were to just quickly look at those branches structure, we've got it branch 0 and 1, and there's multiple items in each branch. So what we've actually produced there is a 2-dimensional matrix, which means that we should be able to flip this matrix using the vanilla flip component. Flipping that matrix will then give us per node point both costs. So in this case, this node point here is either 13 meters from one fire exit or 36 from another. And we're just going to simplify this particular calculation because the Australian rules does state there needs to be some conditions met in terms of minimum distance from both for some buildings. But in this case, we'll skip over that because we'll be here forever trying to make their rules. If we sort each of these lists and pick out the first item from each one, that'll give us the smallest number, which means flattening that. Actually, let's not. Well, yeah, flatten doesn't matter. Flattening that, plugging that into the gradient system means that we've got 2 points now, and that'll give us the best value from those 2 points, and we should be able to add any number of points to that system. To to be able to work out if we're good or not. So in this case, we've got far too many fire stairs. Ooh. Three might be too much. I'm going to put a quick clean tree in here just to because the system's breaking. So this guy here, if we place him, that entrance just there, and then, let's just start there. That's not going to work, so we probably need a fire stair at least there. And that's covering our floor plate. Is everyone clear on that? That quick little script that I did with the flip matrix and the sort list and this list item? Okay. So, we're gonna now do some analysis using the graph to work out, okay, if we pick a certain field of points and we do this analysis on them, which ones would be best? So, for example, this guy here, this is a far more efficient place to put a fire stair from a fire safety perspective because we have. Just delete this one. Because our average distance is smaller than if we were to put it sort of like on one of these extremes, right? So there's a few methods that we can use to try and work this out. We could use the average. So the average distance between the average cost of all of these costs here is 26 meters. And if I move this point over here, it's 32 meters. So, there's a far more efficient system there. But we can also weigh our points to say, well, how many points are over the maximum or under? Oops, and the maximum will be 40. So that'll give us true false values. I've spoken to you guys about if you convert true falses into numbers, the trues they become ones and the falses become zeros. It becomes really useful if you just want to count how many trues there are. If you convert them to integers and then do mass addition, that tells us there's 401 nodes that are under. If I move to that corner over there's 336, so on and so forth. There's 324. Okay, so we can, if we've got these metrics we can use, then we can technically run these calculations multiple times. So rather than doing a single source shortest path from 1 point or 4 points, we could technically do it from all of them. Now, before I do this, I'm just gonna fire stairs graph theory, and I'm going to then grab a series. We're going to go count how many points there are. So there's 527 points. I'm just going to quickly put a x divided by 4 into this, just so we're going to do a quarter, just to see roughly what happens. So plugging that in, that quarter of those sampled points takes 194 milliseconds. So we're good. So if I reckon if I set that to no expression, that's less than a second's calculation for to calculate every point in that sampled set. Now just remember, I am doing this to 2 meters, so this is going to get a bit slower as we reduce that sample. But you're best off doing that sampling, that higher grain sample work after you've worked out the script and whether it works or not. So we've got our costs here. We can run them through our averages, and we can also run them through our number of nodes connected formula, which is the slower one. And that's giving us, this metric, this average metric of 35 meters versus these scores. So what we can do is these map exactly the same to those nodes. So each branch is effectively, branch 0 is associated with node 0 in the mesh. So we should be able to do the exact same thing we've done here, where we've shown like a constructed mesh with a gradient, that gradient being controlled by the distance from a single point. We can use that to show, okay, I'm going to grab the maximum and minimum of the averages. We break them apart and plug them in. The values we want to use are those averages, and we can construct another mesh using those colors to show us, those efficient average points, right? So in this case, this zone here, and this is quite obvious, but this zone here is the best place to put a fire stair exit. And we can do the same thing with these this is obviously going to be the different scale, because we're counting how many nodes we get to. We could invert it this way, but this is producing a very similar similar graph to the average, which is basically suggesting that the best place to put a fire stair is at that corner. So do you guys see why this might be an important exercise to produce? Because you could have we could change our let's change our floor plate. Hate Revit. Let's just draw it here. Oh, it's going to take a while. Could you go once more from the series? Okay, yeah, give it a second. Isla, Isla, do you want to say hi to the class? You want to come say hi? Come here. Come on. You come around. Yeah. Come on. Come here. Okay. There we go. So it's telling us the obvious, but as well, it's quite useful um, information just for a very quick analysis. Like that's gonna save quite a lot of time. Now, from the series, is that what you're saying, Tom? At this point? Yeah. Okay. So see, what we were doing here is we're getting a point. We're testing what index that point is at in the cloud, and we're using that index to work out the shortest path to every node from that. Rather than picking one, what we've done is the series is telling us, okay, we're gonna basically create an index for every node. So that's what the series is doing. So it's, in this case now there's 1,522. Let's just pop that back to the other floor plate. So we've got our 527. So what we're doing is we're doing that exercise for the 1 point for every point. So there's 527 branched trees that are coming from every node, and we're measuring the weight and cost of all of those. And in this metric, we're just taking the average. So the idea that if you were to just say, well, take every path, so there's 500 paths, and you average them, a position on the floor plate that is closer to every other point is going to have a lower average than one that's further away than to some. So, and that's why with this averaging system, we end up with, this guy over here is the most inefficient place to put a fire stair, and this point over here is quite inefficient, but it's not as inefficient as this point or anywhere along this wall. So we really want to be focusing on that there. The average system is averaging per branch. So the branches are being defined by each node's shortest path. So they line up. So if we just flatten the tree and get the minimum and maximum bounds of the numbers, so in this case, the averages are ranging from 23 meters to 55. Rather than using these sort of like fixed values for our deconstruct that domain, something just made a noise. We can deconstruct that domain so that any value that exists in that flattened tree is going to be mapped from left to right. And then we can move on from there. We could technically also, just to think about this, we could also put in 40 meters as the maximum. What that does is it says, so this, what it's doing is it's least shrinking the bounds of the analysis so that at least like this guy here has enough points, enough pathways that are less than 40 meters versus more than 40. You know, if you with averages, so like if I had 5, 5, and 15, then the average will always be smaller than 10. But if I had 5, 5, and then like 115s, then my average is going to be way higher than 10. So yeah, we could do that as well. But yeah, it's really this really comes down to like how you want to analyze your system. You have to create the rules for the analysis. Um, Hello, you've decided to come say hello to the class. Come on. Can you say hello? Are you going to say hello? Huh? Are you going to do some grasshopper with us? So, yeah, we've. Does that explain it, Tom, or not? Do you need me to explain this part as well? This is just a different like analysis system. Can you just hover the script for 2 minutes? Like, like so? Damn it. This part. This part. Is that an? Yeah. Cool. Does anyone have any questions? No questions? How about what's just have a think. Um, whilst people are kind of just reviewing the script, what have we kind of ignored that might exist on a floor plate? Yeah, obstacles. So walls, columns, potentially furniture, right? So, uh, what what we might do, because it's getting to about 11 o'clock. Um, shall we try and we'll try and have a break. 11 is that yeah? It's been 2 hours. Let's have a break. In the meantime, maybe have a go at drawing some obstacles in Revit. So like walls, maybe a void. I don't. Uh, how would you draw a void? Leo, can you suggest a way that I could draw a void in this slab? My Revit's so awful. I don't know how to do that. Yeah. Yeah. What? To, s- oh yeah, this one. So let's say yeah, we've put a someone's decided to put an atrium here. I think it is. I can see the. Yeah. We'll just draw some line, like draw some walls in. I'm gonna go grab something to eat. Um, so it'll be about 30 minutes break. But yeah, draw some walls in, and we're gonna like the you can see this void has obviously picked it up because we're picking that up in Rhino, um, because we're grabbing the floor slab. But if you draw walls, that's not going to eat into the slab because the walls will sit on the slab. So we just need to we're going to do some geometrical functions off the Revit model. Um, so if you draw some walls and maybe some chairs and furniture, we'll add that in. Yeah, cool. Look, this might seem really dry, but I can tell you now, this stuff's like there's a step towards being able to use computational design to do solve real world problems. No, which one are you talking about? Oh, that one. Yeah, I know that one. I hate that video. But yeah, go on. No, no. Like we had Autodesk come in and they were like, "Oh yeah, we've solved generative design. Like, you know, we've done this generative design thing. You guys can do generative design now with Dynamo." Um, and I'm like, I I feel like I feel like you don't understand what the problem is with generative design. It's not the fact that the computers can't do it. It's that it just doesn't fit with like design process. Generative design is the process of defining high level goals and constraints and then using the power of computation to automatically explore a wide design space. Blah, blah, blah. For the designs of a new Autodesk office space in Toronto, we started with the constraints of 3 floors in a new building. Yeah, go on. And the constraints of program, including meeting rooms, social spaces, and the number of people that will work here. And then we're gonna use different measurable goals. How how do you know people's work style preference? You have to survey them? Yeah, yeah, go on. I'm sick of reading out the video now. Yeah. No. Look, Spiderweb's a plugin that makes it's a plugin that makes graph theory easier in Grasshopper. If you can go find graph theory libraries for Python. There's a whole bunch for Grasshopper. There's one called Space Syntax, but I find it's a bit too user friendly. There's others called there's another one that I find quite useful. Um, no. Yeah, that's another one. There's this one. It's called Sandbox. It just basically gives you like the adjacency connections between things. Graphs are so simple in terms of how you can communicate them. Like it's basically just saying there are there are 10 nodes and then this is the instructions for connecting the nodes. Connect 1 to 2, 2 to 3. So a lot of graph theory plugins, they can work with each other, because as long as you can convert your graph back to just a set of simple instructions, they work together quite well. So this is actually the sandbox one. I use that to sort of break down a graph and just focus on like one node or and what the valence is. Valence meaning like the connections between node to node. And you'll see this terminology sort of in all this mesh stuff. I shouldn't get distracted. I should go to lunch and get something to eat. Yeah, but hang on. So you can see here, mesh edges with a valence 1, meaning they've only an edge which only has one polygon connected to it is going to be naked, because any edge that has only one can't have one on the other side. Edges with valence 2, which means there's 2 adjacent faces, and then a mesh. Like if you have a mesh that has 3 faces coming off one edge, that means that mesh is broken. So any edges with valence 3 or higher, they're going to be non-manifold edges that are breaking the mesh. So you'll start to notice this sort of graph theory stuff pop up in computer science a lot more now that you know that it exists. Okay, 30-minute break. Let's see what I can get from my apartment in 30 minutes. See you guys. It'd probably just be a bacon and egg roll. See ya.